Hi everyone, we are Team 12. Today we are going to propose a new combination of technologies which are In-Situ fibrillation and foam injection molding for producing lightweight composite foams. I'm Annie. I will provide you with some background of the project. As the development of the automobile and aviation industry, the demand for high performance and lightweight materials has dramatically increased. This is because many studies have shown that the weight of a vehicle is proportional to its energy consumption, bringing a huge impact on our environment. As a result, more and more companies in the industry has begun to replace conventional parts made from heavy metals like steels and aluminum with lightweight composite foams. One of the most popular lightweight composite is fiber reinforced composite, which use fiber as a reinforcing component filling in the polymer matrix. The biggest advantage of this type of composite is that it has relatively low density while maintaining high performance in terms of strength, stiffness, and so on compared to other materials. Currently, common types of fibers used are classified under synthetic, natural, and hybrid fibers, of which synthetic ones are the most often used. In the existing fiber-reinforced materials, carbon fiber-reinforced polymers are well known for its superior performance and also its high cost. Typically, the tensile strengths and modulus of CFRPs are around 2,500 MPa and 200 GPa respectively. Furthermore, the most commonly used fiber is glass fiber because of its low price, which is about 90% lower than that of carbon fibers. However, glass fiber has a poorer performance and higher density than that of carbon fibers. The main drawback of these fiber-reinforced composites is that they are not recyclable as some other polymers. To address the sustainability issue while maintaining the performance, using natural fibers is a promising way, but the difficulty of industrial implementation is a big problem in the field. Next, I will pass to Ben. He will talk about the conventional process of making fiber reinforced composite.
Some of the conventional processes to make fiber reinforced composite includes injection and extrusion molding. The high throughput and versatility makes these processes widely seen in the industry, but the fibers of choice are usually limited to carbon or glass fiber. Hand layup is another popular process to create laminated parts. The products are stronger but denser, and the throughput is generally lower. Additive manufacturing is one emerging advanced manufacturing process. Its major hallmark is its customizability, and that applies to printing different phases of matrix and fibers with great precision. However, the loose interlayer bonding use weaker mechanical performance. Through preliminary research on the conventional materials and processes, we find that the increased environmental regulations and general awareness makes products like carbon and glass fiber reinforced composites less desirable. Currently, the manufacturing scene is trying to explore new strategies and processes to reduce greenhouse gas emissions and pollutions. In that regard, the focus for automotive industry is still on lightweight components to improve fuel efficiency and reduce carbon footprint. Then there is a need for advanced manufacturing process for lightweight components that decrease energy consumption and raw materials used. That can also replace existing materials and processes. To see actual implementation, the advanced manufacturing process should ideally be able to sustainably produce components that performs as good as carbon and glass fiber reinforced composites. The density should remain low to not hinder the fuel efficiency, and the throughput needs to be comparable to conventional processes so manufacturing firms are not turned away by the downgrade. Now I will turn to my teammates to discuss the technical details.
So the proposed design is to use in-situ fibrillation to create fiber-reinforced polymers with enhanced material properties. This includes the mechanical properties, the thermal resistance, and the crystallization effects to promote barrier properties. This is required to reduce the need for expensive fillers such as graphene or glass fibers and carbon fiber. The goal is to quantify the increase in performance after material processes have been proposed. This is done by combining the fibrillation with foam injection molding to manufacture parts with multiple geometries. On the bottom left, you can see the process for microfibrillation, and the bottom right, foam injection molding. The resulting material from the processes proposed will be evaluated with materials such as CFRP. The basis of this comparison is to analyze the enhancement of material properties, the cost effectiveness, and the quality of parts produced. The bottom is an example of a common reinforced polymer such as carbon fiber.
Fiber-reinforced polymer composites can be produced by a process called in-situ fibrillation. This involves melt blending two polymers to produce a uniform dispersion. This blend is then stretched to produce in-situ fibrils of the dispersed polymer within a polymer matrix. This is done industrially using rollers or blown gas to stretch the polymer. Here, I'll outline three high-throughput methods of in-situ fibrillation. These three methods are melt spinning, melt blowing, and spun bond. Melt spinning is a displacement control technique used to produce fibers by Godet rotation. This uses a single screw extruder to melt a well-dispersed polymer blend. The molten polymer is then flowed through a spinneret die and then stretched by rollers. Although these fibers possess good mechanical properties, this is a multi-step process that can often involve substantial operator intervention. Melt blowing is a one-step process to produce superfine fibers. With this technique, the polymer is extruded through a die and is then rapidly compacted into fine fibers by a hot stream of air. This is a single-step process that produces weak fibers. As well, the use of heated air increases operational costs and process risks. Spun bond is a one-step manufacturing technology used to produce fibers with similar diameters to melt spun fibers. This process uses cold air to draw and freeze the well-oriented fiber and fiber structures, imparting improved mechanical properties. This process uses cold air and does not add significant operational costs or safety hazards. After ranking each process in terms of operating costs, environmental impacts, mechanical properties, and safety, the spun bond fibrillation process was selected.
Foam injection molding is a method of producing lightweight polymeric foam materials. It is similar to conventional injection molding, but involves the implementation of supercritical gas to produce parts containing voids. There are generally two classifications of foam injection molding: low pressure foam injection molding and high pressure foam injection molding. In low pressure foam injection molding, the molten polymer is saturated with gas, and the saturated polymer gas mixture is directly shot into the mold cavity. The bubbles are then nucleated within the mold cavity, and this will form fairly non-uniform parts, but it will have very short cycle times. In contrast, high pressure foam injection molding includes the extra step of packing before the final foaming occurs. This packing allows the nucleated gas to redissolve before mold opening to allow the gas bubbles to expand. This produces parts that are very homogeneous with enhanced mechanical properties. However, this technique does involve the extra dissolution time, which is approximately 20 seconds, which is extra compared to low pressure injection molding. The foam injection molding technique selected for our design is high pressure foam injection molding. This method was selected because it imparts high market value of the foam materials, as they will possess enhanced mechanical properties due to both the fibrillation process and the foaming process, which produce more homogeneous structures. Now let's move into the final design. So the final design is the combination of the spun bond fibrillation technology and the high pressure foam injection molding technology with mold opening technique. So the fibers are produced with the spun bond, and then they're transferred into the foam injection molding machine to produce parts in a similar fashion as mentioned previously. However, the synergistic effect of the spun bond fibrillation technology and the high pressure foam injection molding technology with mold opening technique possesses many limitations. Firstly, the spun bond fibrillation technology alone has limitations in that the material compatibility, viscosity ratio, and processing parameters must be controlled to accurately produce fibers of good diameter so that we can have good mechanical properties. The second issue is the actual implementing or inputting of the fibers into the injection molding machine. In many cases, it is necessary to add an intermediate step to make a master batch of fibrillated pellets and then implement those pellets into the injection molding machine. This will help smooth over the transition and facilitate a faster process.
As you can see from the table, the proposed solution provides similar mechanical properties such as the density, the tensile strength, and the modulus of elasticity. While all this is done, the cost is significantly reduced, and this can be optimized with further foam techniques to enhance these numbers even more. And to conclude, the demand for lightweight materials that are enhanced is increasingly important, as many car and aerospace manufacturers are looking for more efficient systems. However, the cost of materials such as carbon fiber is very expensive and not widely used. The proposed solution is to combine in-situ fibrillation using the spun bond method with high-pressure foam injection molding to create these products. This results in superior mechanical properties at significant cost reduction versus the other reinforced polymers. The future of this technique is important to implement into mass manufacturing and to conduct more lab scale studies of the material properties enhancement versus other reinforced polymers.